kid that's pushing a toy. So there's this kid that's pushing a toy, and the toy has a mass of 1.00 kilograms. And we're going to push this toy across a rough floor. With an applied force of 8 newtons. We'll just make it to the right. And the toy's displacement I'm going to keep it another nice round number, is going to be 5 meters to the right. As always, it's a smart thing to draw a free body diagram. I want to ask the question, how much work does the child do? I know some people thinking ahead are thinking like, oh, what about the friction? Forget about the friction. I want to ask a straightforward question. How much work does the child do? We know how hard the child pushes, so how much work do they perform? We start off with our old equation, work equals force times displacement times cosine of theta. And we know that if the displacement is to the right, along with the force applied, we know something about that theta right off the bat. So delta D is equal to 5 meters, force applied is equal to 8 newtons. So we can start subbing in our values, and work is equal to 8 newtons times 5 meters times cosine of theta. And if they're in the same direction, what's theta equal to again? 0. 0, 0, 0, if they're going in the same direction. So cosine of 0, and I think we know by now. What's cosine of 0 equal to? Yeah, that's 1. Okay. So 8 times 5, nice round numbers. How much work does this kid do? 40, yeah. 40 joules. You know, people might do the intermediary step where they say, oh, that's really 40 Newton meters, and then they make the recognition, oh, Newton meters and joules, same thing. We're going to jump straight to joules. Okay, so the kid does 40 joules of work. Now I want to do a part B. And so this kid was pushing a toy across rough floor. So now I want to throw in the idea of friction. We're going to sort of do a few things together here, okay? So part B is going to be, how much work does friction do? Okay, so I'm going to take away this. I'm going to fold it in half. So that we have our original value still. And I want to know how much work friction does. I'm going to redraw the free body diagram. If you have it on your page, you don't necessarily have to, but we've got our F normal, we've got our FG, we've got our F applied, and now we didn't put it onto our free body diagram initially because we weren't even thinking about it yet. But you know, really, the full free body diagram for this one should also have force due to friction acting backwards on the free body. Is it kinetic or static friction? Yeah, kinetic. Why? Why is it kinetic? Yeah, it's moving. It's sliding. Clearly it's moving because it moved a total of 5 meters. So we can say that it's Fk. Now I chose some really sweetheart numbers here. What's Fg equal to for a 1 kilogram object? Yeah, 9.81. I'm not even going to show the math for that one. 9.81 newtons. If it's on a horizontal surface with no angled applied forces, what's the normal force going to be equal to? Yeah, 9.81 newtons. And we could put in the applied force here. Happens to be 8.00 newtons. Not sure that it's going to make any impact at all, but we'll put it in there anyway. Now, if I want to know the kinetic friction force, I'm going to calculate that first off. Fk is equal to mu k times the normal force. We can start subbing in some values. We said that or we haven't said the coefficient of friction yet. I'm sorry, I need to tell you that. So mu k for this scenario is equal to 0.50. And it's unitless. So kinetic friction is equal to 0.50 times the normal force, which is 9.81 newtons. I think I used this kinetic friction force in a previous question, but yeah. 4.905? Okay, 4.905 newtons, and I can label it on my FBD, 4.905 newtons. And so when I go to find my work, I'm back to the same old thing again, and I say work is equal to force times displacement times cosine of theta, same old, same old. I'm running out of space. Can I bump the question off? Get rid of this thing now? Okay. Slide her up, give us some more room here. Work is equal to 4.905 newtons times a displacement which was 5 meters in the original problem, times cosine of, now here's that question again, if I've got friction going to the left working against me and I actually achieve a displacement to the right despite friction, what's the angle between them? 180, yep. So cosine of 180 degrees is what we're looking at here. Cosine of 180, and of course you know that cosine of 180 degrees is -1, yeah. So 4.905 times 5, help me out guys. 24.525 joules, or rounding to sig figs. I think we have 3 sig figs. Oh, wait a minute. It's 2. Dang it, because of this silly thing. Let's give ourselves 3. Thank you. Negative. And to 3 sig figs, 24.5 joules. Now there's a part C to this. Because if we've got, and this is the last one we're going to do, okay? If there's positive work and there's negative work, do you think there's such a thing as total work? Hey, if you know how much positive work something had done to it and how much negative work something had done to it, can you figure out how much total work there is? Yeah. Well, let's see. Well, we're going to do work total. We'll call it work total, okay? So part C. Find the total work done on the toy. And we don't even have to draw a free body diagram for this one. We could say, hey, look, the total work must be equal to the sum of all the works done on something. So work due to friction in this case, plus work due to, I don't know, kid. And we found the work due to friction was equal to, what was the work due to friction anyways? 40.0? No, that was the work due to the kid. Negative 24.525? And the work done by the kid was that 40? Yeah, okay. 40 joules. What's 40 minus 24.525? 15.475 joules. Nice. So this toy had 15.475 joules, or approximately 15.5 joules worth of work done on it. All told, after all the friction and all that stuff is considered. Okay? Now, there's